Let us continue our nonlinear analysis techniques that we started in the previous class, and we looked at the linear and nonlinear problems in the previous class. And now let us look at one more class of problems, that is in terms of the materials having some limited strength. Let us say we have materials with certain limit, and like our elastic plastic materials, and we already know our Mohr Coulomb yield surface. In terms of C and phi, we can define this yield surface that limits the strength, and if any Mohr circle falls within this surface, it is an acceptable stress state, and if it crosses, then that means that your stress is more than the strength of the material, and we have to do something to remove those stresses, so that the stress becomes acceptable. And so we need to correct the stresses back to the yield surface, and so when you correct the stresses back to the yield surface, your equilibrium is going to get disturbed. So in this class of problems, we need to satisfy not only the equilibrium, but also certain given yield condition. The yield condition is simplest one is our Mohr Coulomb yield condition with this yield surface in terms of the C and phi. And so it is not easy satisfying both the yield that is based on the strength of the material and also the equilibrium. So we need some type of an iterative analysis so that we can satisfy both. And so we rewrite our equilibrium equations in terms of incremental form, but then our incremental form is written in a slightly different manner. Kt du is the applied force P external minus B transpose sigma, right. The previously we had written the equations like this. Simply written the incremental stiffness matrix multiplied by du is dP, and that dP is only the applied pressure, and we did not bother about the calculating the reaction forces, because anyway they will be equal to the applied forces. But now because of this yield condition, our the calculated stresses may not satisfy the equilibrium. So we need to do or form the equations in a slightly different form, and we do calculate the reaction forces as B transpose sigma, and this summation is for all the elements in the mesh, whether it is continuum or a joint element or a bar element or anything. We calculate the reaction force and then sum them up, and the P external is the applied load that is applied on the system, and then this is the reaction force, and the difference is our incremental load. So our dP that we defined earlier is now the difference between the externally applied load and then the internal reaction, P external minus P internal corresponding to the I minus 1. See, the I is the current load step or the current iteration, I minus 1 refers to the previous load step or the previous iteration based on the stresses that we calculated until the previous analysis or the previous step or the previous iteration will give us this reaction force P internal. Okay. And we need to repeat the solution several times until our P external and P internal are nearly the same. Okay. And we monitor that in several ways. One is by monitoring the out of balance force. The dP, we can call it as the out of balance force, that is the difference between the external force and then the internal force. And we are not going to do this at each and every degree of freedom. We can do it in a global sense by calculating some norm, and this could be it's a ratio between the squares of all the unbalanced forces divided by the squares of all the applied forces, and this is the numerator. We have sigma of dpi square divided by the applied forces square. We take a square so that we have everything as positive, like because our forces could be negative forces, the reaction also could be negative, and but if you take everything as positive, we will end up with only a positive convergence number psi 1. This multiplied by 100%, and an acceptable convergence norm is the norm of the out of balance force should be about 0.1 to 0.5%, and in some highly nonlinear problems we may not be able to reach this level of convergence. We might increase it to 1% tolerance or something. Then the other way of monitoring the solution is through the incremental displacements. So every time you iterate, because of your dP, you will have some incremental displacements. So if dP is very small, your incremental displacements will be very small, and so our psi 2 is the norm of the incremental displacements is the sum total of the ratio between the sum total of the squares of the incremental displacements divided by the sum total of the squares of the total displacements, and this multiplied by 100%. And once again we aim for about 0.1 to 0.5%, so that our solution is as accurate as possible. And how do we achieve this type of equilibrium? And it is a very expensive process, because we need to repeat the analysis several times, and we may have to also iterate several times to maintain the equilibrium. And there are different methods called as initial stress method, tangent stiffness method, or a mixed method, a combination of initial and tangent, and then a secant stiffness method. Then there is another method called as the initial strain method, also called as the viscoplastic method, but this is not discussed in this course. Actually, in the initial strain method, what we do is we temporarily allow the stresses to exceed our yield limit, and then gradually dissipate them with some using some viscoplastic algorithm, and then that excess stress is leading to this to the creep strains. Okay, actually, in the case of elastic plastic, we deal with the plastic strains, whereas in the case of viscoelastic or viscoplastic, we have the time dependent strains like the creep strains. And this initial strain method is not discussed in this course, because we are not dealing with any creep or viscous response. I will explain these different methods: the initial stress method, tangent stiffness, and then a mixed method, as of course is a combination of these two, and then the secant stiffness method. So among these methods, the initial stiffness method is the fastest. In this method, the stiffness matrix is kept constant, and the final strain state that satisfies both the equilibrium and the yield condition is obtained by iteration. We perform several iterations until we are able to satisfy the equilibrium and also the yield condition. See, the advantage of this method is very fast, because we form the stiffness matrix only once and assembled and inverted only once. See, the entire analysis, the stiffness matrix calculations for all the elements and their assembly, and then after we assemble the stiffness matrix, we make it as an upper triangular matrix, that is the inversion. We do it only once, and in the iterations we only do the back substitution, which are very fast. Those calculations are very fast. Okay. And as we iterate, we get the incremental deformations just by mere back substitution. And the steps are like this. Let's say your stress strain curve is something like this. It's a highly nonlinear stress strain curve, and then we have applied a stress of this much, and this is the converged state where you are exactly matching with the stress strain equation, and this is your strain at this stress, and at our disposal we have only the initial modulus, initial stiffness, or initial modulus, and corresponding to that is our initial stiffness equation. So, if you apply this stress and calculate the displacement or the strain, we get an epsilon 1, and but then corresponding to epsilon 1, the acceptable stress is only this much, and this is the unacceptable stress. See, we can the material can only support this much stress at this strain level, and so this is the out of balance stress, and corresponding to this we need to calculate a reaction force and then repeat the analysis, and if you apply the force corresponding to this unacceptable stress, we will get some incremental displacement epsilon 2, and then we continue, and in all the iterations our stiffness matrix is going to remain the same. So, the slope of this line is remaining the same, and as we proceed along, your out of balance stress will go on decreasing, and then at some stage we will have a converged state. So, the analysis proceeds like this. K multiplied by dui is pi, that is applied, minus pi minus 1 internal, and pi is the applied force, like for example our stress that we applied, and the internal reaction, that is because of the stresses that are allowable within the material. Okay. And integral b transpose sigma I minus 1 is your pi minus 1, and so as we repeat the analysis, our out of balance stress will go on decreasing, and your incremental displacement will also go on decreasing, and at some stage we might have convergence. Okay. dui is k inverse times p applied minus p internal, and ui is ui minus 1 plus du, right, and d epsilon is b times du, and epsilon I, that is the total strain in the current iteration, is the strain in the previous iteration epsilon I minus 1 plus the incremental strain d epsilon, and our total stress the incremental stress d sigma is d elastic multiplied by d epsilon, and our sigma I, that is the stress at the end of this iteration, is the stress in the previous iteration d sigma I minus 1 plus the stress increment that is produced in this increment. d sigma I. And then once you get this new stress state sigma I, we check for the yield condition, and if it is not satisfied, then we correct it back to the yield surface and then calculate the vector of unbalanced forces, and then repeat these calculations until our norm of the outer balance forces, then the norm of incremental displacements, they reach some constant value. Okay. So, now let us apply this to a simple equation, because I am going to demonstrate all these through simple hand calculations, because if you do through finite element programs, we will not really know what is happening. And let us take a stress strain equation like this. Sigma is 600 epsilon minus 1200 epsilon square, right? And this is our constitutive equation, and the slope of the stress strain curve is E tangent d sigma minus by d epsilon, that is 600 minus 2400 epsilon, and the initial modulus EI is 600, okay, because if you substitute epsilon of 0, E tangent is 600. So, EI is 600, that is going to remain constant throughout the analysis. And now we are interested in knowing the strain corresponding to a stress of 65. Okay. And what we have is we know that the initial modulus is 600, and your stress strain equation is sigma is 600 times epsilon minus 1200 epsilon square, and then the tangent modulus is 600 minus 2400 epsilon. And let us say we apply this the first time, okay, and the 65 by 600, and we get a strain increment of 0.1083, and our strain is 0.1083. So, if you substitute this back in our stress strain equation, we get a stress of 50.803. But then we have applied a stress of 65. So, the out of balance stress is 65 minus 50.803, that is 14, and you apply this back on the system. So, 14 divided by EI, that is 600, that is 0.02347, and the total strain is 0.1083 plus this value 0.13, and the stress as per our equation is 58, and the outer balance stress is 6.76. And so, you go on repeating this process, and each time we are maintaining the same Young's modulus of 600, then we are calculating incremental strains, and then the total strains, and then the stress as per our equation that is given. And you see, as the number of iterations are increasing, your outer balance stress is decreasing, and your total strain is also converging. Okay. And we continue until we reach some convergence. Like let us say we want the outer balance force to be within about 0.5% accuracy or 1% accuracy, and so on. Okay. So, this procedure will take a very large number of iterations, because we are maintaining a constant Young's modulus. The Young's modulus is kept constant at 600. We can improvise this by using the tangent stiffness method. So, in this method, the stiffness matrix is updated at every iteration based on the current stress state, and the stress state at each integration point goes on changing during the analysis, because as you apply the loading, you will have some deformations, and these are different at different elements. So, at each integration point we calculate the stresses, and then form our constitutive matrix dt, and our tangent stiffness matrix kt is integral b transpose dtb, right? And so this tangent stiffness matrix we have to formulate at every iteration, and then we have to make it as an upper diagonal matrix and then back substitute to get our displacements, because the right hand side we have the outer balance force, the pt minus rt or b transpose sigma, okay? And so this is actually, it's a very highly involved process, and we need lot of time and effort. And this tangent stiffness method requires lesser number of iterations, because at each step we are estimating the new slope of the stress strain curve, okay? So let me explain that. See here we have this nonlinear stress strain equation or the stress strain curve. We applied some stress, and we want to know what is the converged strain, and so for that we initially apply with the initial modulus, we get some outer balance stress, and then we update our stresses, and then we get a tangent modulus like this, and then once again the tangent modulus at this step and so on. So within a few steps we will see that we reach the converged state as compared to initial stress method. So the only difference here is we are using this kt instead of k. In the initial stress method, that k was remaining constant, whereas here we are updating it every iteration and every step, okay? So our stresses are computed finally, and then we check for the whether this particular stress state is within the yield limit or not. If not, we do the corrections and then repeat the process, and then we check if the new stress state sigma I satisfy the yield condition. If not, correct it back to the yield surface, and then we develop some unbalanced force, and then we apply this back on the system and repeat the analysis, okay? And so this is actually it's a slightly faster method, or it takes lesser number of iterations compared to the initial stress method, because we are updating the stiffness matrix. And once again, let's do one hand calculation to illustrate this. And our E that we are calculating here is similar to our stiffness matrix. This we say this is actually, it's a single degree of freedom system. So for the single degree of freedom system, your modulus itself is your stiffness matrix, because you can get your deformations, okay? So our E tangent in this case is d sigma by d epsilon, that is at 600 minus 2400 epsilon, and then our initial modulus is 600, and the applied stress is 65, okay? So at the end of first iteration, 65 by 600, that is 0.1083, and our strain is 0.1083, and the stress is 50.905, and then the outer balance stress is 65 minus 50.905, that is 14.09. And now we calculate the tangent modulus in terms of this strain 0.1083. So the equation for tangent modulus is 600 minus 2400 epsilon. So our tangent modulus is now 340. So to start with, we started with an initial modulus of 600, then at the end of the first iteration it has come down to 340. So now we calculate the strain increment in terms of this updated tangent modulus. So 14 is the outer balance stress divided by 340, Previously we had only 14 by 600, now we have 14 by 340, that is 0.0414. The total strain is 0.1497, and then the stress is 62.94, and then the out of balance stress is only 2.05, and then we calculate our updated modulus. So, our updated modulus at the end of second iteration is 240, next it has come to 220, and then it has come to 219. You see that it is getting closer and closer. So, in the second step, instead of using 600, we use only 300 for the module, 340 for the modulus. So, our strain increment is this, okay, and our total strain is this, and our stress is 62.94, and the out of balance stress is 2. And you see at the end of the fourth iteration, we are able to reach a stress of 65, and then the converged strain state of 0.1587. And once you see that there is no out of balance force, we can just simply stop. And this particular tangent stiffness method, it has converged within 4 steps, whereas let us look at the initial stress method. So, in the initial stress method, even after 6 iterations, we still have some out of balance force 0.80. It has not come down to 0, whereas in the tangent stiffness method, it has come down to an out of balance stress of 0, practically 0. Okay. And there is another method called as the secant stiffness method, wherein our modulus is the secant modulus is calculated as sigma by epsilon. So, our sigma equation for sigma is 600 epsilon minus 1200 epsilon square. So, our secant modulus is sigma by epsilon. So, that comes to 600 minus 1200 epsilon, and once again the initial tangent modulus is 600. So, our initial strain increment is 0.1083, and then the stress, if you substitute this back in our equation for stress, we get this, and the out of balance stress is 14, and our secant modulus is 600 minus 1200 times 0.1083, that is 470. So, in the next increment, when you calculate the incremental strain, the out of balance stress 14.08 divided by 470. 470 is your secant modulus. So, 0.0299. Okay, total strain is 0.1383, and the stress corresponding to this strain is 60.02, and so on, like we can continue until we get a good equilibrium. Okay. And the advantage with the secant modulus procedure or the secant stiffness procedure is that our secant modulus will never become negative. See, even if you are doing this type of strain softening analysis, what we do is we calculate at each and every strain softening interval, we calculate the secant modulus as the stress divided by the corresponding strain. Okay. And now let me illustrate this with an Excel spreadsheet. Yeah, I think I forgot to bring my Excel file, but I think that we will do in the next class. The first thing that we will do in the next class is I will illustrate the procedure through an Excel spreadsheet, the initial stiffness method, and then the tangent stiffness, and then the secant stiffness, so that all these 3 procedures are clear for you. And then we are going to follow the same procedures even for our finite element analysis. Okay. So, the advantage with the secant modulus method is the secant modulus will never become negative. So, we have the ease in the numerical computations. Okay. So, I think that may be my the summary is see, in this we have explained all these 3 procedures using a single degree of freedom system, where the stiffness matrix and then the modulus are synonymously used, because we have only one value, so that we can easily do the computations. But similar procedure can be used even in the finite element analysis, and I have used the stress and the force synonymously, and then the strain and displacement are also used synonymously, because the displacement is just simply strain multiplied by some length. Okay. And so, I will demonstrate all these 3 procedures using an Excel spreadsheet, so that you understand the difference between each of these methods, and then you can solve some problems on your own using these spreadsheet programs. So, thank you very much. So, if you have any questions, you please send an email to this address profkrg@gmail.com. Then I will try to respond back to you as fast as possible. So, thank you very much.